Oh, well, yeah. Well, first I want to say thanks to the team for organising this challenge, as the last presenter did, and putting this all together, especially in such difficult circumstances. So I know they've had to change various ways that they've done things because of this pesky pandemic that's going on. So anyway, I'd just like to introduce what I'm going to talk about. So first, I want to explain my motivation, why I entered this competition. And I'm going to talk about the approach that I carried out. Then I want to talk and explain what a Unet is. So I seem to be the only participant who has used this particular technique. This could well have been my naivety, but we'll see how we go. I'm going to explain what the Unet is, and I'm going to explain how, in order to address the 5 millisecond look-ahead restriction, I used a window processing approach. I'm going to talk about how the Unet was trained, the hearing model I used, and then some results and conclusions. So my motivations for entering this competition may be slightly different to the other participants, although this first one is probably ubiquitous. So I'm more familiar with classification and regression problems in audio machine learning, and I was really keen to learn more about some deep learning approaches in audio processing. And it's helpful to have some external deadlines imposed on you to force you to kind of learn about these things. So that was my kind of first motivation into why I was interested. But also I have an interest in hearing loss from the point of view I have relatives who are hearing aid users. This is important to me. It's important to a lot of people. And I have done some research in the past into audio quality for the hearing impaired, though I don't have any experience in hearing aid signal processing. I also had a bunch of parts left over from a PC I took apart, and as a personal project, I wanted to build a deep learning workstation. So this is not so important, just the fact that all training was carried out in my garage. So an overview of my solution. As some other participants have done, I've downsampled to 16 kilohertz, as I felt this would have minimal impact on speech intelligibility, but allow me to meet the memory requirements that I have had from my particular system. I split my algorithm into 2 parts. First, I had the noise reduction, which was just simply reducing the noise, irrelevant of what the listener was, and then a listener adaptation as a hearing aid here. So just to kind of give you an overview of what Unets are, as this is the first time we've looked at them in this in these presentations. So these were first introduced in 2015, and they were introduced for biomedical image segmentation. So these are convolutional neural networks. If you're not familiar with these kind of networks, you may well be, but they're particularly suited for image analysis. So what we have is an image as input, and the network predicts what we call a segmentation mask. And this is something that gives meaning to different parts of the image here. So in this case, is this a cell or is this not a cell? Importantly, for this context, the output is the same dimensionality as the input. So in 2017, this publication here from Jensen et al. Demonstrated that you could actually use the Unet to do musical source separation. So given some mixture of audio, calculate the spectrogram of that audio, the Unet can then predict a mask, which you then apply to your input spectrogram, and you can mask out parts of the sound. The idea being that you can have multiple networks and multiple masks to then isolate different sound sources. In this case, it was just a singing voice. Interestingly, the original mixture phase is used in the reconstruction here. So I'm now going to just explain an overview of the Unet architecture in the context of what I actually use. So this is the actual structure I used. So the input to my model is in the form of 6 seconds of audio from which a spectrogram is computed. This spectrogram, the shape of this, I have 376 frames and 513 unique frequency bins, and I'm using all of the 6 microphones here as well. I zero pad the input so that it is a power of 2, and one of the aspects of the Unet that is important is it performs this continual downsampling as you travel through the network. by a factor of 2, and then this continuous upsampling by a factor of 2. So having the dimensionality being a factor of 2 is quite helpful. So the Unet consists of basically 2 paths, and it's called a Unet because it basically, the diagram looks like a U. So firstly, we have the contracting path, or we can call it the encoder. And this is effectively just a traditional convolutional neural network, which you might use for image classification. So what we have is a number of steps, where at each step we have this max pooling operation, which effectively halves the resolution of the image. In this case, it halves the resolution of the spectrogram. And then the number of filters is doubled by a factor of 2, until we end up with this low resolution representation of the spectrogram, which we hope captures all the salient information about that particular input. In the next stage, what we have is, call it an expanding path here, or the decoder, where what we have is the resolution is continually doubled by these upsampling layers here. So we can see it's continually doubled, and the number of filters is halved at each step as well, until we end up with the dimensionality, the same dimensionality as the input here. We then add a final layer. In this case, this is a 1-by-1 convolution with ReLU activation. And what I did here is I trained it to predict the enhanced magnitude spectrum directly. So rather than a mask, which is what was used previously, I happened to train it on the enhanced magnitude spectrum directly. A key feature of Unets, and something that was mentioned similar to the last presenter, is these skip connections. And these are connections between layers in this encoder, the contracting path, to the same hierarchical level in the decoder, in the expanding path here. And what this does is it allows information to flow directly from the high resolution input to the high resolution output. If you were to do this upsampling without using these skip connections, if these didn't exist, what could happen is you can end up with displacement of pixels, or in this case, displacement of bins or frames. And in spectrograms, as you might imagine, this is a particular disaster where you can have shifting of frequency bins and jitter in terms of the frames. So it's these skipped connections that seem to allow the Unet to operate so effectively. So of course, I can't process six seconds of audio all at once. So in order to kind of meet the 5 millisecond causality restriction, what I'm doing is this window processing approach. So what I do is I define an input sample window of 80 samples with a hop of 70. So what we've got here is the current input in red, and then the input from the previous frame, the overlap of 10 samples there. Then what I do is I expand the input to include any samples that have occurred previously in the past. If there's no time history available, then I just use zeros, just a zero pad. And my thinking behind this was in the Clarity data, there's always, as we know, there's always some of the interferer on its own before the target utterance occurs. So this additional context is going to give the network some extra information about what the actual the interferer looks like. So I made an animation. There we go. Forgot to play it. So we have this input processing window here, which is going to form the input to the Unet. I process all 6 channels simultaneously. So my input is 96,000 samples by 6 channels. This is 6 seconds. Calculate a spectrogram on each of these inputs, pass it to the Unet. And interestingly, I only train one Unet, and I train it only to estimate the enhanced spectrogram at the left ear. I don't train it to enhance the spectrogram at the right ear, only the left ear. I'll explain that in a second. I then perform an inverse short-term Fourier transform, again using the noisy phase just from the left ear, and I end up with an output processing window of 6 seconds. Then I only take the last 80 samples of each of these output processing windows and use overlap add reconstruction to kind of form the final output here. So in terms of training Unets, I synchronize the clean target with the noisy channel. In particular, I synchronize only with the first channel of the left ear. And what I end up with after window processing is a huge number of spectrograms, 1,372 pairs of inputs and targets. And in order to actually get my computer to train, I randomly undersample this. So I only have 10% of these examples remaining. This works because actually the Unet is calculating an output independent of which input it is. It's just based on whatever it sees. I'm training using TensorFlow. Again, Adam optimization, and for my loss, I just use mean absolute error. I planned to look at others, but time got the better of me. I had to stop training after 22 days as I was concerned about my electricity bill. So this is a new form of early stopping that I'm using here. So for the left ear, inference is carried out on all 1,372 spectrograms. We pass it into the Unet, which then predicts the output of the left ear. We use the inverse short-term Fourier transform and then overlap add reconstruction as previously indicated. So this is how the left ear works. For the right ear, what I do is just a little trick where I mirror the head by swapping ear channels around left to right. And effectively what I'm doing is I'm taking a mirror image of the head, and now I can just get the Unet to predict the output at the left ear again, knowing that it's actually right ear that it's estimating. And this kind of takes advantage of fact that within the Clarity training data set, the interferer was located at a large number of positions all around the head. So it's kind of seen, the interferer has seen a number of positions, or it can be mirrored at least anyway. So for my hearing aid, my original plan had been to just use the open MHA hearing aid implementation provided. But from what I understood from the documentation, and somebody may be able to confirm this or not, is that the look ahead was rather more than what I had remaining. So I implemented this instead, rather late in the day. What I did, it was an FIR filter bank consisting of a series of zero-phase FAR filters. These were rather short, 11 taps with a 5-sample look ahead to make sure I was overall within the rules. So unfortunately, this resulted in a somewhat compromised listener adaptation. So firstly, I had to combine all of the lowest frequencies below 2 kilohertz into a single band. As people will be aware, this is actually some of the most important energy in speech for intelligibility. So that's not brilliant. And then also the bandpass filters are not great. Due to the length of these filters, there's a significant amount of overlap. So I then used the 2-channel compressor provided in the Clarity Challenge repo just to control the level. This is operating on the broadband signal after the filter bank has been summed. And then a soft clipping processor just to limit the, just to prevent digital clipping. I hadn't intended to submit multiple entries. So here's some results. I decided to do the same analysis as the baseline paper for comparison. So I'm splitting results into 1 decibel signal to noise ratios, calculating the average NB-STOE measure. Green squares are the noise interferer, red squares are the speech interferer. So this is for the proposed model. And then for the baseline, what we have here is the circles, the same color. And what we can see, there's a marked improvement over the baseline. Interestingly, the improvement is greatest at lower signal to noise ratios. So that's nearly 0.2, and that's less than 0.1 up here for noise, and similar for speech here. I also calculated the correlations. So there's a much lower correlation between the NB-STOE measure and the signal to noise ratio, indicating this is a bit more robust to the signal to noise ratio than the baseline model. And then also I noted that there was this kind of, there's the speech and noise much closer. So there's less of a difference between speech and noise for this model than the baseline. So overall for the dev sets, I can see an improvement we saw of about 0.15 for the MB-STOI measure over the baseline. And then for the evaluation data set, there seems to be a much larger improvement of 0.35. I need to do more investigation to understand why that is, or perhaps somebody can comment. I was interested to know the baseline is quite lower. I guess this is probably to do to the difference between the speech and noise cases. I'm not sure, perhaps somebody could comment. And then in terms of the percentage correctness from the listening tests, we have a marked improvement of about 23% here. What I also did was I evaluated, this is evaluated over a subset of the data, just purely due to time constraints. I had a look at my proposed model with and without the hearing aid, just to see if it was actually making much of a difference. And what I found, there was an improvement, so it is helping. There's an improvement of 0.03, which is fairly marginal, but it is doing something, so that was good. So some conclusions quickly. So I've presented a method that improves over the baseline for the MB-STOI measure and for the percentage correctness, although we need to wait for the final results for that. My hearing aid model was rather compromised, unfortunately, due to some of my design choices and time. So there's definitely work to be done there. I've released all the code on GitHub, as well as all of the models. And what's here I found incredibly helpful was there's a Docker image as well, which I found particularly useful. So I can see I'm running out of time, so I did have some further work, but I will skip that. Thanks for listening.